TUBS-IRMB, Digital India, Educated India.
Okay, then welcome to the 9th lecture in this GIAN course on high fidelity lattice Boltzmann methods. Today we are talking about the more, say, efficient, we start talking about more efficient models than the BGK model that is kind of, just a introduction. Now we want actually to deal with, because this course is on high fidelity methods, we are here specifically interested in increasing efficiency, especially for large scale simulations. And in order to understand what we have to do for this, we first start with talking about efficiency. So I may have told you that all the different ways of implementing collision operators. So so far we have just seen the BGK version, but this was just an approximation where we have many moments and we deal with all the moments the same way. Now we want to deal with different moments in a different way. And I told you in principle they can all solve the same kind of problem. So what is the difference? The difference is in their efficiency. When you have a method that is either more stable or more accurate, you can do the same thing with lesser resources, at least potentially. Either the same thing with lesser resources, or you can do better with the same resources. And now we look on how this actually works. So in general, fluid mechanics, computational fluid mechanics is always has the problem that it is too expensive. And we are relatively confident that this problem is not going away. Because whenever we have a faster computer or a better method or whatever, the problems that we are facing in doing fluid mechanics simulations is always bigger than we can actually afford. And this will go on for the next 100, 200 years. So computer gets bigger, still we want to solve bigger problems. So minimizing the cost of computational fluid dynamics simulations will always stay to be a problem. So now what we are going to do is a little bit modeling the cost. And for this, we introduce a few variables. So we speak about the computational cost that we call C. Speak about the domain size that we want to simulate. And in this domain size, we call the domain size V, and by this we mean the volume. So of course it makes in the modeling a difference whether you count the volume or the length of a domain. This will scale differently. And then we have a duration, D, so this is time, and this is the time that you want to simulate, not the time that you need to do the simulation, but the time that you want to simulate. For example, you want to simulate a starting turbine, then this will take 0.5 seconds or whatever until it is in a state that you could regard as steady. So, and then we need for our code also a performance measure. Performance measure P, and this P in the lattice Boltzmann world comes in so-called node updates per second. So how many nodes you can update in a second. So this depends on your code, and it depends on your computer, and this is called NUPS, node updates per second. And this is basically calculated as P is the number of lattice nodes times the time steps that you want to calculate divided by the wall clock time. So the wall clock time now is the time that your simulation, the wall clock time, am I still audible? The wall clock time is the time that you have to wait until your simulation is done, yeah, in your office playing games. So the number of lattice nodes, as we talk about volume here, the number of lattice nodes we call n, and this is of course the volume by the grid spacing cubed. The number of time steps t is the duration of the simulation divided by delta t. So then the computational costs can be stated as the number of nodes times the number of time steps divided by the performance, which then can be written as the volume times the duration by the performance divided by delta x cube and delta t. So what you observe, and which is probably not so surprising but still not appreciated enough, is that delta x has a much larger impact than delta t. It's very logical. However, one thing that you should notice is it's always much simpler to change the time step than to change the grid spacing. Because if you change the grid spacing, you have to, redo all your mesh. Yeah. So making your, but you should know that you should not try to make your simulation so much more efficient just by increasing the time step. This is not the biggest handle that you have. So we have, of course, on these things, so in principle you would like to make the grid spacing as large as possible and the time step as large as possible, but of course there are some constraints, and they may be very important. So what are our constraints? Obviously, accuracy is our constraint. And that's actually worse than it looks like. So we need these things to go to zero. Okay, so talking about accuracy. Yesterday we talked about asymptotic convergence, yeah? And the thing with asymptotic convergence actually is that we don't really use it in reality. And the reason for this is, again, because CFD is too expensive. Now, in principle, you can talk about asymptotic convergence only when your physical problem is absolutely resolved. Only then do you actually have convergence. Otherwise, you are under-resolved, and so as long as you are under-resolved, you don't really have convergence. So speaking in terms of turbulent flow, you would only start to talk about convergence once you resolve the Kolmogorov length everywhere, and then you refine, and then you see convergence. Yeah? Before this, if you have not resolved the Kolmogorov scale, you will never actually physically see convergence. So this actually is a big problem to us, because this means that there is a physical constraint, not a numerical constraint, but a physical constraint on delta x and delta t. Yeah. So otherwise we only see what we resolve. Other things we cannot simulate. And we often do not resolve everything. Funny enough, it still gives often reasonable results, but you know, this is luck, not ingenuity or something. Okay, so beyond the physical things, we have the numerical things. Of course, we have the CFL condition that we have to fulfill. This means there's also max speed. Max speed, by the way, also means that time step and grid spacing are coupled. Yeah. And then something that's of importance today is that we have a minimal viscosity. So usually there is a viscosity beyond which the method is simply no longer stable. And now let's look at this, because this is important for us today. So the kinematic viscosity, how this is defined. So somehow we said that physical quantities I write with an asterisk. So I now mean here the physical kinematic viscosity that I can write as theta. So I have to get this by theta 1 over omega minus 1/2, and then it needs to have a physical unit, and the physical unit is the delta x square, which now comes, delta x comes now in meter and delta t comes in second. So this is the unit of a diffusion coefficient, and this theta is 1/3, with omega being the relaxation rate. So this is our viscosity. And now this viscosity, we want to see what influence this has on our grid spacing and time step. And we can, of course, then write this like this, that grid spacing squared is viscosity times time step divided by theta 1 over omega minus 1/2. We add to this the Mach number. So the Mach number in our simulation is the physical velocity, which again I write with this asterisk, divided by the speed of sound. So this is theta, square root theta, divided by delta x and delta t. Now this will be the Mach number that we use in the simulation. Yeah? So does not necessarily mean that this is the physically correct Mach number, but that would be the one that we are using, because this here is the speed of sound used in the simulation. So you can still scale the Mach number. So we can solve this for delta t now being equal to the Mach number divided by u times theta, square root theta, into delta x. So now we put this into this guy here. So then we have delta x So this delta t into here, then we have delta x squared on one side and delta x on the other side, meaning we can cancel one of them, and then we have delta x is equal to the physical viscosity times the Mach number divided by theta, because we have square root theta, this becomes now square root theta down here, and there's the velocity left, and we have 1 over omega minus 1/2. So this is how the grid spacing is related to both the physical viscosity, the physical velocity, and the Mach number that we are choosing. And now we can put so what are we doing next? We can put this thing, we can put this thing into this here and get dt is equal to the physical viscosity and Mach number square divided by u star square 1 over omega minus 1/2. So now we can express the grid spacing and the time step in relation to what viscosity we have, what Mach number we have, what omega we are using. And this we now want to use in order to see our computational cost. So the computational costs, this capital C, was the volume times the duration, the performance that we have, delta x cubed, delta t. Now we are replacing delta x and delta t to get volume times duration by performance. So we have to take delta x to the cube. So there's this viscosity times Mach number, the square root of theta, we have velocity, and we have 1 over omega minus 1/2. And all of this goes to the third power. And then we have, in addition to this, we have the this here. So this is the viscosity times the Mach number square by u square 1 over omega minus 1/2. Yes, and that's it. And this is, you can rewrite this a little bit to give you volume times duration times the velocity now to the fifth power, 1 over omega minus 1/2 to the fourth power, and p nu star by the fourth power times the Mach number to the fifth power, and this becomes minus, is it really minus? Yes, it's minus theta. Okay, we could put it on the other side, but this is a constant, it's not important. So do I have everything? Okay, now there are constants in this which are just given by physics. Yeah, I mean, you have a problem that has a certain volume, you have a certain duration, you have a certain velocity, and your stuff has a certain viscosity. So this is not under your control. This is the given by physics. So the things that are under our control is 1 over omega minus 2 to the fourth power and the Mach number to the fifth power. So you have actually scaling the Mach number, yeah, because we are solving we are approximating an incompressible Navier-Stokes equation with a compressible one, yeah. Not using the right Mach number, but scaling the Mach number actually gives you a pretty big handle, because this goes with the fifth power in your performance. Yeah. But one thing I mean, but you can go only so far with the Mach number. I mean, you still need to be much smaller than 1. Yeah. So actually, if you think about this, we had this in Germany. Cars go by 230 kilometers per hour on the highway. Normal. So what Mach number is this? 0.3, right? 0.3. So there is not. Lattice Boltzmann cannot do much more than 0.3. So actually, there's only so much you can do with the Mach number, but apparently with omega you can do a lot, because if omega goes to 2, this here will disappear. It will disappear with the forced order. So meaning our performance depends a lot on how close we get with omega to 2. The closer omega is to 2, the lower the cost. Yeah? Here, again, I have to remind you, here we ignore that this changes the resolution, and that the resolution is also bound by the physical problem that we want to solve. If we do not resolve our problem, then we may be efficient, but we don't necessarily get the correct result. But anyway, getting closer to 2, then for example, with the BGK methods, helps us with gaining a lot of efficiency. So what's again about the only method that so far we have looked at, the BGK methods? Here we have a post-collision state that is made up from the pre-collision state plus omega Fijk in equilibrium minus the pre-collision state. So this is the lattice BGK collision operator. And now when we assume that omega goes to 2, then what we have is twice the equilibrium minus this pre-collision state, and this is the no. You see, this is now completely symmetric. Yeah, you can just put this here on the other side, 2 times the equilibrium on the other side, and then you can run the same thing backward. So this is the omega is to 2 is the no dissipation. Is the no dissipation limit that we cannot reach. And those of you have implemented the code already and tried a few things out, you will see that BGK with omega larger than 0.9 is often unstable. I think that BGK with the moment matching equilibrium is usually stable until omega equal to 1.95, which is already much better than the BGK with the Taylor expanded equilibrium. But still, I mean, everybody has to have a cold today. Still, there's a lot of room for improvement, obviously. So now the big question that we've already spent half an hour asking, how to get closer to omega equals to 2 without losing stability. Okay, long motivation today. let's look at what we had yesterday in our asymptotic analysis. With our 2D BGK, lattice BGK. So we had dt m10 to the first order plus dx dx m20 to the second order plus dy m11 to the second order minus omega 10, so this was the forcing term to the 0, is equal to 0. And inside this, we had that m10 to the first order is rho 0 to and u to the first order, and m20 over bar to the second order was m20 equilibrium to the second order minus 1 over omega minus 1/2. And here we had this omega 20 to the second order and m11 to the second order, m11 equilibrium to the second order minus 1 over omega minus 1/2. And here comes theta. This is not beautifully written. There's a theta. Omega 11 to the second order. So why I'm writing this again? The observation that we have here is, so here appears omega, yeah, for the Navier-Stokes equation. But this omega that appears here, that we need, so this is the BGK omega, this only comes with second order, or with second moments. So the Navier-Stokes equation itself puts no constraints on the relaxation of all the other moments. It only puts the constraints on the relaxation of the second moments. So we are kind of, either we are kind of stupid or kind of lazy with BGK, that we use the same relaxation rate for all the other moments too. Probably we are lazy. We just say, so we don't have any constraints on the other moments, on the relaxation rates for the other moments. We have the constraint that they are not conserved, right? So they have to relax. However, we don't know by which rate, so we just take the same rate as with the BGK. Now it's the question, is this a good decision or is this a bad decision? And actually, this decision has advantages and disadvantages. But we have to look into the detail. Okay, first we have to see what else we can do, and then we have to see what problems that causes that are actually not present in the BGK. So, as I just said, just writing this down, BGK acts on all moments. So the nice thing is we do not have to separate the moments because we treat all of them the same. So now the idea that we have is, let us relax the different moments with different rates. So first of all, let us identify which we need to keep. So we said that there's this omega 1 to second order. So this actually has the value, if you remember, dx v to the first order and rho to the 0 order plus dy u to the first order and rho to the 0 order. Then there was this omega 2 0 to the second order, can be written as rho to the 0 order, so I keep this outside, dx u to the first order plus theta dy v to the first order, which of course can be written in a different way, because we know that according to our asymptotic expansion analysis, the divergence of u is 0, and here we have a combination of these two. Yeah, so there could be, this can be rewritten, and actually we can also rewrite this by adding these 2 seconds moments together like this. So then we get one theta for dy and dyv, and 1, so to say, yeah, from we have 1 plus theta in front of all of them, so we have dx u1 plus dy v1. Okay? So, and this we identified to first order. This is 0. And by the way, this now is not an approximation. It's not approximately 0, yeah, because this is already first order written here. So to first order, it's exactly 0, right? So approximation, the thing that later in our life makes it only apparently approximate is that we do not have u1 and v1. Yeah, we have only the entire series of u1 plus all the error terms together with it. Yeah, but for this relationship here is exact, and because it is exact, because this thing here is exactly 0, it actually disappears from the Navier-Stokes equation, and therefore it does not constrain the relaxation rate of these 2 moments together. So there are second moments in the BGK equation, but the sum of these two second moments, they are not in the lattice in the Navier-Stokes equation arising from the BGK equation. Therefore, there is no constraint on their relaxation rates.
Excuse me, sir.
Yes.
Why you are adding omega 02? I mean, it.
Omega 0. Where do I put omega 0?
Omega, sorry.
You mean rho?
This ohm symbol.
Where's 0?
Yeah, there only.
So omega 20 plus omega 02?
Yes.
Why I'm adding them?
I mean, from where you are getting the term omega 02? It doesn't appear in the governing equation, right?
Yes. Okay, that's true. It does not appear in the governing equation, but you can. So I mean, you have another governing equation for the other direction. Yeah. And
Okay.
in the other direction, the other omega appears. So what I wanted to point out is that the sum of the two disappear. Yeah. So this doesn't mean that it individually disappears. So then, what is left if the sum disappears? Then the difference still exists. Yeah. So I write the difference down in a minute. Yeah. I just wanted to write here down that this here. Okay, in any other order. So this does not show up at leading order. You are completely right. This is not in the governing equation, but this doesn't keep me from separating it out, because what I have to do now is to say that the difference between the two So this thing here, the second order, is 1 plus theta rho 0, and here we have the difference between the two, dxu to first order minus dyv to first order. Now this is not 0, yeah? So this omega 2 0 minus omega 0 2, this influences the leading order. Meaning, we can now distinguish for the second moments the following relaxation rates. For M2 0 plus M0 2, we define a relaxation rate omega p, because this is actually the pressure. Then for M2 0 minus M0 2, we use omega bgk. And for the moment M11, we again use omega bgk. So these two use the bgk omega that adjusts the viscosity, and the other one, we have the freedom to choose it in any other way. So let's see what else moments do we have, and let's group. Let's do some grouping of the moments for the D2Q9 lattice. There we obviously have M00, M10 plus an M01. So these are the conserved moments. These we do not want to relax. Then we have M11 and M20 minus M02. These are the so-called non-conserved hydrodynamic moments. They are called so because they are required to solve the Navier-Stokes equation. Non-conserved hydrodynamics, so they need to have omega bgk. Then there is this M20 plus M02. So this is actually the pressure, or it's called the acoustic moment. In acoustic scaling, this thing is not 0, and you can actually do pretty good acoustics with this. So you can, we simulate in an organ pipe, you can then make this audible, and actually it sounds like the organ pipe. Yeah. So nowadays also this is used in automotive industry to simulate actually the noise generated by driving vehicles. So this here we're using omega p, and this omega p is related to what we call the bulk viscosity. Bulk viscosity in the real physical world is notoriously difficult to measure, and it's not really a natural constant. So the bulk viscosity is the damping of pressure waves, and this depends a lot on what you have in the air. I mean, whether you have dust in the air, whether you have droplets in the air, whether you have, you know, when there's fog, the moisture, humidity, depending on the condition of the air, this will change over several orders of magnitude. So it's very, very difficult to determine what this actually is. Yeah, but this, so what it does is it is damping of sound waves. So I mean, there are some people who say that if you don't put this to the BGK value, then you don't do the physically correct thing. But it's very, very difficult to know what is the physically correct bulk viscosity because it depends on so much different things. So then this has not been all the moments. We still have M21 and M12. This we set omega 3 to this, and we have a fourth moment M22, M22, where we put omega 4, and these are our ghost moments, where there is basically no direct constraint on the relaxation rates. So now what you could do, so the first thing that you may want to do, and I have to warn you that this is not necessarily the best thing to do, but anyway, this is, if you have no other idea, please, take the mic.
So just one clarification. So here when you say that there is no restriction on the omega values, which of them you are particularly saying there is no restriction?
Yeah, so there is of course restriction on these two here. They have omega BGK. Yeah. So, and all the others are not related directly to the solution of the incompressible Navier-Stokes equation. So I really say that there is no restriction on it? I mean, yes, there is no direct restriction on it, but there is the stability restriction that they have to be between 0 and 2, right? So this, they need to be between 0 and 2, and they need to be far enough away from 0 and 2. Now give me an arbitrary number somewhere between 0 and 2, sufficiently far away from 0 and 2. 1. So now what you could do, yeah, it's not the best solution, but what you could do is you put this to 1, yeah, and then you get pressure waves kind of suppressed, and there are always people claiming that there's all the magic behind MRT, that you suppress the pressure waves, and I think this is not true. I mean, this can be a step in order to get it more stable, but it's not true that this is the only effect. Yeah. Then suppressing of these ghosts. There you could also put omega 3 to 1 and omega 4 to 1. Again, this is not necessarily the best solution. Yeah, in particular for omega 3, there are better solutions. But this is what you could do if you have no better idea. Okay, so let's briefly look at the classical MRT that you will find in the books, or rather in the papers. So this was introduced by Lalmand Lu in 2000 in PRE 616, page 6546. So this is a classical paper in the Lattice Boltzmann world, and this introduces the MRT method in 2 dimensions. So this was done back then using a transformation matrix. At least in theory, it was done like this. In practice, they don't use transformation matrix. And when we come to the hackathon this afternoon, I suggest that you're not using a transformation matrix. If you want to use a transformation matrix, okay. But I rather say do it in another way. This is not efficient. So Yes, so what was important, there was an orthogonal matrix. Not also normal, but also orthogonal. So you transfer two moments giving this matrix. So you multiply this matrix onto a vector of populations. So this is a moment vector, and this is a population vector. So I'm telling here you a little bit of history. So what we do is the streaming. So we cannot just use moments, because moments do not stream. Yeah? We need the populations for the streaming. But then the collision is done on moments. Okay, no, collision, collide. Collide moments. So what you need to do is you do the streaming, then you do a transformation to the moments. Once you have the moments, you do your collision, and then you have to retransform. You have to transform this back to the distributions, and then the distributions can stream. Okay, so this was actually an unweighted. So this is later becoming important. It's an unweighted orthogonal. Unweighted is important. Unweighted orthogonal matrix M was used, and the D2Q9 moment system now looks like this. And I mean, this is a classical thing. So it's from 2000. It's 25 years old. We don't do it the same way nowadays, but I'll tell you how it was perceived, and you may look into papers and think this is a good idea. It was supposedly a good idea. Maybe it is a good idea compared to what was there before, but nowadays we do it in different ways, because we know it. We have somewhat better ways of doing this. Anyway, so they found an order. You know, this guy is Lou is a Chinese. Yeah, so they don't like to have something like writing down things with simple script. For every word they need an own letter, and this is pretty similar here. Yeah, so I hope everybody here appreciates that there's countable moments that you can just count up. They had a completely different idea. They thought about every moment in detail and said, so this has to look like this, and this has this physical meaning, and this has to have this name. So the first moment, the zero moment that they have, it has the name rho, which is the same thing that we also have. Then they name one E, which is related to the energy, basically the pressure. Then they unfortunately have something that they call epsilon, which is a forced moment, or the forced moment, and is related to the energy square, because they could not come up with anything else what it could mean. Then, I mean, they are not, okay, see, this is zero moment, second moment, forced order moment, and now comes this first order moment. They are not ordered here by their countable, order. Jx is the momentum in x. Yeah, it's velocity times density. Then there is Qx. This is a third order moment. Then there is Jy and Qy, and then comes the things that are basically second order moments again. So all of this can be expressed in terms of countable moments, which I'll give you translation here. In countable moments. Yes, so rho is the only one that is simple. Oh no, there are three that are simple. Rho is M00. Then there is E, that is 3 times M20 plus M02. So this here obviously is related to the pressure. And here comes minus 4 M00. So this is actually, you see, this is not just second order moment, but this is second order moment minus zero order moment. The reason why this is like this has to do with the orthogonalization of the matrix. Yeah? So they define different moments here. But this is related to the acoustic moment. Then we have this epsilon, which is 4 times the zero moment minus 6 times M20 plus M02 plus 3M22. And this is a ghost moment. I hope you get an idea why I don't like this. Why does this look like this? Zero moment, second moment, fourth moment. All put in one moment. Jx, now this is simple. This is M10. This is, of course, a conserved moment. And then Qx is 3M12 minus 2M10. This is again a ghost. Then we have Jx, which is simply M01. It's conserved. Any question? Then there is Qy, of course, looks the same as the above, M21 minus 2M01 is a ghost. And then we have these things that now are related to, these are now the hydrodynamic, the non-conserved hydrodynamic moments, Px and Pxx and Pxy. These are the hydrodynamics. So what does, oh, we are writing English, sorry. What does unweighted orthogonality actually mean? I think we touched on this already, but I repeat, unweighted orthogonal. So say, okay, now we have a moment, say we have a moment with a kernel phi, yeah, m phi, that is the sum over ij, phi ij into fij, and say we have a different moment m psi that comes with the sum over ij, phi ij into fij. Then these two moments are said to be unweighted orthogonal. If the sum over ij, phi ij times psi ij, if this is equal to 0. then they are called unweighted orthogonal. So, as an example, to see that this is the case, we look at E. E is 3m20 plus m02 minus 4m00. This is now the sum over ij from -1 to 1 into Fij. Now, how do we write these moments? M20 obviously is I square. M02 is obviously j square. And M00 is just 1, so this will be -4. So, which means that there is a moment phi ij is 3i square plus j square minus 4. And this now is supposed to be orthogonal to all the others. We are just looking now at rho. Rho is equal to the sum over ij from -1 to 1 of ij. So this psi ij, so what is the psi ij here? It's just 1, right? So it's just 1. So when we now make the sum of the two, I and j from -1 to 1, psi ij times phi ij times psi ij equals to, well, this is almost cheating because psi is always 1, so it disappears. What we have left with is 3i square plus j square minus 4. This times 1. Now we have to sum this up. This will give us 3 times. So we'll have actually 6 times, yeah, the I in the, so this is like, so how many, so you have actually nine populations, and out of them 3 have no I in them, yeah, so there will be 6 with left, and 3 have no J in them, so this is what is left, and we have 4 times all the 9, and you see that this is 0, and therefore they are unweighted orthogonal. So, and 11 years ago, I was on a Lattice Boltzmann conference and gave an invited talk on the last day, explaining to all these guys that this is nonsense. And actually, Li Shilu, the author of this paper, later, I mean, they disturbed the talk, but later he stood up and said, so we'll make sure the paper will never be published. So the paper got published, and now he also knows that this is nonsense. So there is no reason why you want to have this type of orthogonality. They could never explain why they want to have this type of orthogonality. And actually, this does more harm than good. But we will see. Okay, I just said it does more harm than good. The advantage here is in 2D is that due to the low number of moments or rather of ghost moments that you have in 2 dimensions, means that orthogonality actually has very little effect in either direction. So it does not make it much better, and it does not make it much worse. So this is something that I want to write out so that it's not forgotten. So the orthogonalization has It has some effect that you can also see, but the effect is not large. And the important thing now is that this is very different in 3 dimensions. Okay, so one dangerous thing that you should never think in fluid mechanics. You've solved a problem in 2 dimensions, and I know here with your exercise here you'll only do 2 dimensions now, yeah? But you should never think that when you have solved a problem in 2 dimensions in fluid mechanics, that you have any idea whatsoever how you solved the same problem in 3 dimensions. Yeah, these are completely different beasts. So, now we talked about 2 dimensions. Now comes D3Q27, 3 dimensions. Okay, now there is a fun thing to notice. There is no classical MRT in literature for this lattice. Guess why? You know, I think it's the following. You try this out. You try the same procedure for the D3Q27 lattice. You run it and you see it doesn't work. And it doesn't work at all. It really, really doesn't work at all. And then you just say, okay, I have made some mistake. I don't find it. Actually, in 2 dimensions, everything was fine. Now I did it in 3 dimensions. It just doesn't work. Yeah. So the problem is the theory that we used in 2 dimensions is already broken, and you just don't notice this in 2 dimensions because 2 dimensions is too forgiving, and in 3 dimensions it just doesn't work. So what works in 3 dimensions, if you have a lattice with reduced number of speeds, so for example with D3Q19, yeah, you get a workable solution, and with D3Q15 you get a workable solution. But if you just apply the same theory to D3Q27, you don't get a workable solution. For whatever reason. Now, let's see whether you'll understand this at the end of this course. We'll try it out. So first thing, what we have to do is we have, again, to find a grouping of our moments in order to see what moments we can distinguish with our relaxation rates. So basically the idea is that we want to find as many different kinds of moments as possible, so that we have as many degrees of freedom as possible, because for every type of moment we can set a different relaxation rate, right? So then grouping of raw countable moments. So we have M00, we have M100, M010. Okay, I'm probably not writing all permutations out now. These are the conserved ones. So conserved means no relaxation. Then we have M110, of which we have 3 permutations. And then we have M200 minus M020 and M200 minus M002. This looks a little bit asymmetric, but it actually isn't. So these are the 5 hydrodynamic non-conserved moments. Here we have omega is equal to omega BGK. And then we have the sum of all moments, which is the acoustic sum of the trace of the second order moments. Yeah, this is the acoustic moment. With omega p, so this gives us the bulk viscosity. So far we are following our theory from 2 dimensions. Now comes many, many more ghosts than in 2D. So, give different categories of ghosts. So third order moment A, this is M120, of which we have how many permutations? 6. 6 times this. Then we have the category 3B. 3B has only 1 permutation, this is M111. Then we have the first order moments, category A is M220, of which we have 3 permutations. And then we have category 4B, M211, of which we have 3 permutations. And then we have the category 5, of which 5 with M221, of which there are 3 permutations. And then there is the 6th one, of which we have only 1 permutation. So these are naturally disjoint groups of moments, but this is not necessarily the best way to subdivide them. Actually, we have to ask whether these can be further subdivided, and they can. So how to do this? What we have to do is to look at the rotations of these things. So we look at the rotation of moments. And in this, what I mean is, so each of the populations has a velocity that we call xi, and they are given by ij, by the indices ij and k, this vector, times delta x and divided by delta t. So these are the discrete velocities. So we can write this as I unit vector x plus j unit vector in y plus k unit vector in z. And yeah, this multiplied by delta x and delta t. Now, this population can be rotated by multiplying with a rotation matrix, so meaning that we get a new I, a new j, and a new k after rotation when we take r. So when we multiply xi by r, so basically this is I, the rotation on x, plus j, the rotation on y, plus k, the rotation on z. And now we can go through all sorts of different rotations due to a little bit lack of time. So I have to squeeze 2 lectures into one here, actually. I'll only talk about the one that are significant for what we need. Yeah. So there's actually much more to say about this, but let's be brief here and say that We just look at the examples that are of importance for us. So let's see, we have a rotation about the x-axis, where this rotation matrix, then when we rotate about the x-axis, we can of course rotate about everything. Yeah, but this would now look like the cosine alpha minus the sine alpha and sine alpha cosine alpha. So you know this as a rotation matrix, yeah, rotating around the x-axis. So, and now we want to distinguish between isotropic and non-isotropic moments. For example, if you rotate the pressure moment, you'll end up with the pressure moment. Yeah. So this, yes, we can look at this. So isotropy, the isotropy of the acoustic moments, so let's call this MP, is the sum over I, J, and K is equal to minus 1 and 1, I square plus J square plus K square, Fij K. So now you do a rotation, and this is actually true for any rotation. With any rotation, you get that I r square plus J r square plus K r square is equal to I square plus J square plus K square, or let's say the sum over all of them. The sum of all of them is the same. So let's see how this works for something else, namely for the third order moments, M12 plus M102 is equal to Fij K from minus 1 to 1 into I J square plus K square, and this onto Ijk. So now let us rotate this rotation about x. So if you rotate this about x, so what we do, I will not change. Yeah, so I will be the same. I will always be the same. Yeah, so the letter I, the index I, will be the same after rotation because we are rotating about the x-axis. But Jr will be replaced by I think probably it's more accurate. I think it's not the equal sign is not right. I mean, this is the replacement. Jr is replaced by J cosine alpha minus K sine alpha, and K will be replaced by J sine alpha plus K cosine alpha. So, meaning that IR JR square plus K, oh, ugly, KR square, so the rotated ones are now getting replaced by I J square. So we take the square of this is cosine alpha square plus sine square alpha plus K square sine alpha square plus cosine alpha square. Now you will see very easily that these guys here are equal to 1, right? So what we end up with is ij square plus k square, and this is exactly the same thing that we had before the rotation. So this does not mean that this moment is rotationally invariant. It only means it's rotationally invariant with respect to x. Yeah? So, but this is already important here, because this is not the case if we had the difference between the two. So they are rotation invariant under rotation about x. So this actually means we now get, or we look at the other one. We look at the other one too. M1 to 0 minus M1 0 2. Yeah, this is IR JR square minus KR square, and this is now replaced by IJ cosine square alpha. Now comes minus sine square alpha plus K sine square alpha minus cosine square alpha. And you see this is not rotational. This is not invariant. Now we have identified that there are two different types of these moments, namely different groups. We have M120 plus M102, of which we have, so the first index is here the same, right? The second and third index is different. Of these, there are 3 permutations, and we attach to them the relaxation rate omega 3 plus. And then we have M120 minus M102, of which we also have 3 permutations. And to this we have omega 3 minus. And actually, if you start optimizing these relaxation rates to get actually a higher order results, what you observe is that these things necessarily have to have different values. Yeah? So we need these things we need to distinguish between these things. So there's something similar going on for the forced moments. So we have M2 to 0 minus M202, of which we have 3 permutations, which we call omega 4 minus. We have M220 plus M202. There are only two. There are only two, sorry. Plus M022, yeah, because we've taken this out. This comes with omega 4 plus. So this again is isotropic, the other one is not. Then there's M211. Again, of these we have 3 permutations. I give this the relaxation rate omega 211. And then we have M221. We give this omega 5. And then we have M222 with omega 4. So what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 relaxation rates. That we can distinguish. Okay, now it doesn't really matter if you set all of them to the same value, obviously, yeah. But we have these degrees of freedom. Okay. Now let us investigate about our unweighted orthogonality. That's actually a problem. And for this, we first recall the asymptotic analysis. Now we do this we've done it in 2D, but we can also do it in 3D. And we look at the second order of MABC. This gives us MABC equilibrium to second order minus 1 over omega. Now we have different omega for different moments, so I'll be lazy and call this omega ABC, also when we may have combinations of these, minus 1/2 dx MA plus 1 BC to now first order plus dy MA B plus 1 C to first order plus dz M A B C plus 1 to first order. So let's look at a specific example, namely that we put A equal to 2, B equal to 1, and C equal to 1. So we're looking at a first order moment. In this first order moment, so this is a ghost. It's actually something that you should not bother about, yeah? But ghosts, is there a folkloric belief in evil ghosts in India? So in Europe we have castles and there are ghosts, people that have not been buried properly. They run around as ghosts and they are usually evil, yeah? So ghosts can be evil. Let's see. M211, yeah, to second order is M211 equilibrium to second order minus 1 over omega, yes, let's say M211 minus 1/2 and dx M311, this is of course now an alien, plus dy M211 to first order plus dz M212 to first order. Now we have to identify these equilibria. This is done by factorization, as we learned. So this is M200 to 0 order times M010 to first order times M001 to first order. Yes, I could write all the other cases too, but you see that M010 has no 0 order. Yeah, the only one of these that has a 0 order term, and then it's related to the density is the M200. Yeah, this is the only one that has non-vanishing 0 order term. This is why I keep it this way. And then we have to normalize this by M000 to the 0 order square, which basically turns out to be theta, namely theta is in this M200, theta, v to the first order W to the first order and rho to the zero order. So this is what comes out here. Then we have this alien M311 to first order. This is equal to M111 to first order, and this to first order is what? This is 0. Yeah? Then this is M212 to first order is actually theta square rho 0 V to first order, and M221 yes, is 1 to 1 theta square rho 0 and W to the first order. So now the way we have written it down here actually works only if we relax the moments directly. So this is actually, I have written here unweighted orthogonality, but this is actually non-orthogonal. Yeah, we have not dealt with orthogonality at all so far. Yeah. Now this is, suppose it is non-orthogonal. Then we can write equation 9.1 as M211 to second order is equal to theta rho 0 V to first order W to first order minus 1 over omega, what do we have? 211 minus 1/2. This goes into theta square rho 0 dx W first order plus dz V first order. Okay, so this is actually the partial differential equation that is equivalent. Yeah, so this is the good thing with our asymptotic analysis. Yeah, we can directly derive the equation for this moment. Yeah, so this moment will always have this moment to this order will always be composed of some velocity part here and this derivative part here. Okay, so what we see here may remind some of you of a different moment that we have already seen, and this different moment is this hydrodynamic moment, which I'm going to write on the next page. The hydrodynamic moment is M011 over bar. Also, we take this to second order, is turning out to be rho 0 V1 times W to the first order minus 1 over, so now that's the hydrodynamic moment. The hydrodynamic moment has omega BGK. Yeah? Otherwise, we don't get them to the Navier-Stokes equation, right? Minus 1/2. Here comes theta rho to 0 order and dx W to first order plus dz V to the first order. So why am I showing you all of this? You may be annoyed. The thing is, if you look at these two partial differential equations for these moments, you see that they look very, very similar, right? So, okay, there is something in front, which the one has a theta, the other one has not a theta, but the more important thing here is this here. So they depend on some derivatives, and they depend on these derivatives in exactly the same way, right? So these things here are not under control because this is the solution of the Navier-Stokes equation. Yeah, you simply have the Navier-Stokes equation, and there's a solution, And even though this is a ghost, and you could say this doesn't matter, it's still there, and this will always be proportional to this, because it has there's the same thing. Now, trouble is, so how can the two be proportional to each other if they have different rates here? Let's have a look. Yeah, let's have a look. What we are going to do is we are now solving this here for the derivatives. So we say that we have theta rho 0 dy it must be y, right? Oh, we are always confusing here. Did I have this mistake somewhere above? No, it's here and here, right? Yes, okay, so sorry. dy, I couldn't read it from my notes properly. So dy w first order plus dz v first order is equal to minus this first moment to the second order plus rho to the zero order v to the first order plus times w to the first order divided by 1 over omega bgk minus 1/2. Now we've said that this equation up here, I believe I said this, yes, so this equation up here is called 9.1. So this is the equation for this first order moment, for the ghost. The ghost just should shut up, yeah? We don't like this guy, he just should be quiet. So let's put this into the ghost and see what the ghost does. So it is, the ghost is equal to rho, theta rho 0 order v first order w first order minus, now if we put everything here, we get 1 over omega 211 minus 1/2 divided by 1 over omega bgk minus 1/2. Into theta comes minus m011. Actually, we could compensate these two minuses together, but I've not done this, plus rho 0 v1 and w1. Okay, so what does this mean? Remember, we have not used orthogonalization so far, yeah? No orthogonalization so far. So these are non-orthogonal moments, and what we see here is that we have this this relaxation rate here, which we said that doesn't matter, and we divide actually by, this is viscosity, right? I mean, up to factor theta, up to factor 3 or 1/3. This is viscosity. So we have here something that we said we don't want to be small, and we divide exactly by the thing that we like to be small. Yeah? So we want this here, this 1 over omega bgk, to go to 0. And we divide by this. Now you see that there's apparently a problem. Yeah, so suppose we have a given M011, then we divide this by viscosity. We want to have viscosity small. Then this ghost here appears to be getting very, very big. Yeah? By the way, here you can, if this is the problem, then you can also see why this MRT works so well with D3Q19. Does anybody remember when we wrote down the moments for D3Q19. So D3Q19 is the lattice that is missing the corners, right? In the discretization of the velocity. So there are no velocities with all three speeds being non-zero. Yeah? So, and if there's always there's no velocities where they are all non-zero. And if this is the case, then the moment M211 does not exist. Okay? So you can cheat yourself out of this situation. If you use a lattice where simply this moment doesn't exist, then you don't have this problem. Yeah? So you can choose a discretization that is actually inferior using fewer speeds that simply does not show this problem. Yeah? But now we want to use this better discretization, and now we have this problem. But this problem is apparently coming from this. The reason for this is, of course, we don't use orthogonalization. So first, okay, let us write this down. BGK is omega. Or what happens in BGK? BGK, omega 211 is equal to omega BGK, yeah, because there's only one. So if there's only one, these two things, this here is not much larger than this here, yeah, because you would have one. I mean, this is both the same, so this here simply becomes one, right? So there's no problem here arising. However, in multiple relaxation times, we want to have, usually, not always, but if you want to have turbulent flow, then you have omega BGK should go to 1, and omega 211 is, could be anything, but should, so let's call this the ghosts, yeah? Omega for the ghosts. So we like to put this, for example, to 1. So this means that our ghosts, this M211 to second order, is a big ghost because this 1 over omega 211 minus 1/2 divided by 1 over omega BGK minus 1/2. This goes to a large value, and then this you simply put this ghost into a position where it has to become very, very large, and when it's very, very large, it will cause you some trouble. So now let us see whether this is the kind of problem we can solve with orthogonality. Yeah, let's start with our unweighted orthogonality. And let's define this moment Mn11 is equal to 3M211 minus 2M011. Okay, I did not derive this myself. What I did, I asked one of the French theoreticians who did all the invention of these methods to give me a matrix for this lattice. Yeah, so they said you have to orthogonalize like this. Yeah, I did not question this. You can now check whether this is orthogonal to all the other moments. Unweighted orthogonal. So this is N211 is just 3N211 minus 2N01. So this means that N211 to second order is equal to 3M211 equilibrium to second order minus 2 M11 equilibrium to second order. And now this is the thing that we relax. Yeah, we are not relaxing the raw countable moments, but we are relaxing this guy, and we say we're relaxing this with omega ghost minus 1/2 rho 0, and here comes now 3 theta square minus 2 theta into dy. This is not an omega, this is W1 plus dz v to the first order. Okay, so this happens if you write, if you use the asymptotic analysis to combine these two moments and then relax it. And now you do again the same thing as before. You replace this gradient term with the second order moment that you have. This gives us 3 times M211 equilibrium to the second order minus 2M011 equilibrium to the second order. We are not looking into the detail what this is. They are just functions of u and v on v and w, obviously. Yeah. And now this is then comes into 1 over omega g minus 1/2 divided by 1 over omega bgk minus 1/2 into 3 theta minus 2 M011 second order minus rho to second order v to first order w to first order. So what did change? Did something change? Indeed, something changed the sign. See, we had the minus sign here, and we have a plus sign here. So nothing, but the original problem still remains, and so this is, no, you're not smiling. You give this a thumbs down because we still have the same problem. We still have the same problem. Actually, this sign makes it a little bit worse. So this is even less stable than the non-orthogonal version. Yeah? And it pretty quickly becomes unstable. So why I'm talking about bad news here only, MRT with unweighted orthogonality is even less stable than non-orthogonal, and non-orthogonal is also not very stable. Okay, so you wouldn't have invited me to give this lecture in India if I didn't present you the solution to all of this. Yeah, I mean there is this problem, but we know how to deal with this. And now at the end of this lecture, I just give you the overview that there is a solution to this. How we find the solution, we'll look into tomorrow. Yeah, but let's see whether we can solve this problem. And because we have now called the thing unweighted orthogonality, yeah, this can only mean that there is also weighted orthogonality. So, and now I let something drop from heaven. Namely, I just propose that I have this moment M211, and I define this moment as M211 minus theta M011. And I tell you, if you want to know why, you have to come to the lecture tomorrow. Yeah, just now. I mean, the things were first solved like this. Yeah. So you see that there is this problem. Then you think, how do I get rid of this problem? So you simply choose a certain combination that will get you rid of the problem, and then you actually think about how can I do this more systematically. But first of all, we look just at we have this problem. Yeah. How do we solve this problem? Yeah. They're saying that there need to be a certain combination that solves this problem. And this combination looks like this. So this moment, M211 over bar to second order, now is M211 equilibrium to second order minus theta M011 equilibrium to second order minus 1 over omega ghost. So we are relaxing now this moment small n211. Now, how does this look like? This looks like theta square rho 0. So this is the prefactor. And what we saw here before, so this has the prefactor theta in front. I mean, the idea behind all of this, if I may go back, yeah, is if you look at the moments themselves, then this guy here, this M211, has a theta square in front of this, and the hydrodynamic has only a theta in front of it. Yeah. So the idea is if I multiply this guy here with a theta, then I get again this theta square. And if I destroy it, what is going to happen if I have theta square rho 0 minus theta square rho 0, right? So, and this now goes into this dy w first order plus dz v first order, but this doesn't matter because all of this is multiplied by 0. So this is in fact not at all dependent on this derivative, because it's no longer dependent on that derivative. It's not going to be large. Now you could say this is a trick, because this just means that this particular moment that we now generated is not large. So what does this mean for the other moments? For the other, because we have just invented this variable. So let's go back and see what this actually means in order to for the other moment. We just evaluate the countable moment. So what does it mean for the non-orthogonal moment? Now we have M211 over bar second order is equal to N211 over bar second order. Now we invert this, so now we have to add theta M011 over bar to second order, which becomes M211 equilibrium to second order plus. So here there's nothing else than the equilibrium itself. been missing something here. So there's M011 equilibrium plus theta 1 over omega bgk minus 1, and here comes theta again. Okay, this is theta squared, theta times theta. dy w1 plus dz v1. Okay, so we have in this moment, we actually have a proportionality to the original moment, but this comes with the usual viscosity. Now it's proportional, but it's of the same size. So this is again a ghost, but now this is a small ghost. It will not exceed in size. It will not exceed in size the second order moment. Yeah, and if you now relax this weighted orthogonal moment, then you will keep stability, and even for these much higher Reynolds numbers. And the way we formalize this, we'll learn tomorrow. So now, as of today, we will have at 2 o'clock this hackathon, yeah. And the idea that, okay, now I leave it with this, and I tell you later what you should do. That there is some. It has a little bit to do with MRT, but it goes a little bit beyond or besides what we had in this lecture. So this is, we meet in this other room. I don't know what, 304. I hope everybody has received the message, and bring all your friends that are still potentially not here now at 2 o'clock in this to the hackathon. Right.